Welcome to the Natural Reward Podcast. I'm your host, Owen Gilbert. Today is September 17th, 2025, and I'm talking to my brother, Jon Gilbert, about inclusive fitness and Hamilton's rule.
In your own work in evolutionary theory, in graduate school, and then your postdoc work, you ran into a fair number of issues with the idea of inclusive fitness and its ability to make predictions that could be falsified. And in trying to untangle some of the issues with inclusive fitness, you went back to the original writings of Hamilton and the original mathematics he used, and you found this to be a very somewhat unapproachable realm, especially that few people had really gone into with a rigorous approach to see if all of the T's were crossed and all the I's were dotted in those equations and how they've been applied. And it turns out in the most recent paper of yours that I read, you were elucidating how Hamilton's own equations and definitions of inclusive fitness had some issues. And there were some variables that may have been potentially misused or had been interpreted by others to be more broadly applicable than they were.
The 64 paper is the one that came up with the concepts. They're not otherwise kind of independently justified. Most people don't understand that paper. Even the experts today, they go on the 70 paper. And I get it. There's so many things about it that made it obscure. One of the first things was Hamilton didn't even say what the point of the paper was until the very end.
What was the point of the paper?
He wrote a summary before he published the paper in 1963 that actually said what the point was, which was to explain the evolution of altruism with Hamilton's rule.
Right.
But in the 64 paper, he doesn't even mention altruism until like page 10 or 11 or something. And then he doesn't give Hamilton's rule until the very end. It's all couched as this new type of fitness. I mean, to me, it seemed like he was creating a house of smoke and mirrors to distract from the fact that he hadn't proved his case very well. So he said all this stuff about fitness maximization and a new concept of fitness. And then at the very end, he gives Hamilton's rule as a special case of the model. You're so lost at that point that you don't even know if he really justified his argument about Hamilton's rule. You don't even know what the point is, really. And there's a number of other things. His model really makes sense as a haploid model.
Well, and this is something you go into in the paper that you shared with me, was that there's a lot of assumptions that have to be true about the organism and the alleles in question in order for that simple version of Hamilton's rule and the equations that he presents in there to work. And that if you take diploid organism or like a dominant gene where there's a dominant allele, then it all breaks down. And then I guess in your upcoming paper, you've told me that you're going to go even deeper into that.
Exactly. But I'll just step back for a moment to say one of the things that was really obscure about the 64 paper, which was that it wasn't clear if you read the 63 and 64 papers, if inclusive fitness is supposed to apply to the gene, to the genotype, or to the individual. Hamilton in 1964 verbally said that it applies to the individual level, and that's a passage that people always cite. Mathematically, in the 64 paper, he says inclusive fitness applies to the genotype. And then in the 63 paper, he makes it seem like it applies to an allele. Later in the 70 paper, he shifted the focus from genes to individuals, using subscripts to refer to individuals. So that kind of solidified this individual level perspective. But at the same time, it took the focus from the genetics so far that I think it became then very difficult to understand really what's going on, because it's most straightforward to do standard population genetics models. You understand the selection on the genotypes. You calculate the fitnesses of the genes from the frequencies of the genotypes and their interactions. The inclusive fitness community tends to take this individual level covariance, variance approach where everything's hidden behind these statistical formulae. Often assumptions are hidden and you don't know what's going on. So in my newer paper, I relate all my equations to those well-known formulae, but I have the population genetics equations to show what's actually going on.
So you're kind of fleshing out to kind of provide mathematical clarity at a genetic level to some of the more broadly used individual level equations that the inclusive fitness community likes to use.
Exactly. And I think that there's a lot hidden there. And so I knew from the way they're using the concept of inclusive fitness to justify adaptationism, or kind of a teleological perspective on evolution, where you see design in nature and then you infer adaptive value based on design, or you say inclusive fitness somehow predicted this when there's no model that actually shows it predicted it. And then you take it as evidence of the theory. Kin recognition is the example that got me onto this, where everybody was taking the finding of kin recognition as evidence of inclusive fitness theory, but it never predicted it, never explained it. And then people were acting like these general equations justify this paradigm. And obviously to me, and it's just a matter of taking the effort to understand mathematically where they went wrong. I do think that it required reading the Hamilton paper really closely and understanding all the links of theory. He calculated a quantity called total fitness, which included the effects of an individual's behavior on itself. It included the effect on kin and the effect on random individuals. And it also included baseline fitness. That was Hamilton's concept of total fitness of a genotype. And then he subtracted from that the effect on random individuals, which he called the dilution effect. So if they're not related, it's like the whole genotype. It's all uncorrelated. If they're kin, related by half the genotype at that locus is uncorrelated. So that sort of dilution effect strikes the uncorrelated part of the genotype. Now, what he did was he said, because in that uncorrelated region, you share alleles randomly, you will share the altruism allele and the non-altruism allele at their population level proportions. Therefore, giving help to that uncorrelated part of the genotype doesn't alter the allele frequencies. It contributes the genes to the gene pool and the ratios that they already exist. So based on that reasoning, he said, well, you can just exclude that and focus on the part that actually changes the allele frequencies. And so in that paper, I was talking about how inclusive fitness is really exclusive because it took total fitness and it subtracted something from it.
Yeah, you're excluding the uncorrelated part of the genotype and any effects on that in your calculation of the fitness. And so you're calling it exclusive fitness because you're excluding this big chunk of what would normally be there on the effect of the quote unquote random or, uncorrelated parts, this so-called dilution effect. Right. So why was that problematic though?
Well, for one thing, you can easily do that in a haploid situation. So this goes back to my point that he assumed a situation of haploidy.
Right.
So if you just have one chromosome and, you just have one copy of the gene at the one haploid chromosome, and you have a social partner, with probably R, you share it identical by descent. With probability 1 minus R, you don't share it identical by descent, but you can share it by state or not share it by state, meaning randomly. You can either randomly share it or randomly not share it. When he split things up like that, it really makes sense for a haploid organism. A diploid organism, you have 2 copies of each gene, you have 2 chromosomes. And so the possibilities are you either share both alleles identical by descent, you share one, at the 2 gene positions, or you share none. You have to consider those probabilities of sharing the entire genotype identical by descent or just portions of it. And he didn't do that in his model setup. If you apply it to diploid genetics, the altruism allele is rare in the population. Most of the individuals in the population are going to be the non-altruists. So all those early generation individuals in a large population with random mating are going to be heterozygous. What that means is you can focus on that one gene because the other one's not the altruism allele. And you can say, okay, what's the probability when it's rare of sharing that one gene identical by descent with the other individual? And you don't really have to think about the probability of, sharing both of them because you can't have both of them. Yeah, that model can apply to that situation of it being rare.
So if it's dominant or if it's not, what difference does it make at that point? Because if you have it at one locus or if you have it on one chromosome but not the other, if it's dominant, obviously that means it expresses. But if it's not dominant but it's not recessive, then what?
That's just the situation of it being additive. You have a continuum. Situations that are easiest to think about is it's fully recessive, it's in the middle, it's additive, or it's dominant. If it's additive, that means that the heterozygote, the one with one copy, is right in the middle of the 2 homozygotes in terms of its phenotype.
Okay, so in other words, it basically is half altruistic or something in its behaviors. It's not as altruistic. It might just do it sometimes or something.
Yeah. And what happens in that case is like, if you think about when it's 50% in the population or something, it's like at every step, it's basically the same situation as when it was rare in terms of like the selective effects going on. But to think about dominance, I mean, for one thing, if the allele is recessive and it's rare, it doesn't get expressed. So it can't even gain an advantage.
Yeah, it wouldn't get expressed. Well, not at first, but if that organism ends up successful and eventually you get situations where it does come in.
Yeah, it would have to have an initial frequency. Like it would have to somehow spread because it's correlated with something that's being selected, or there's like a drift.
Which could happen, right?
There's a population bottleneck and there's an individual with that mutation that happens to have a lot of offspring. It can raise the high frequency. If it's dominant, it can actually invade quicker, but then it has trouble fixing. Once it's really common, there's basically no difference between the heterozygote and the homozygote. So the heterozygote that has the non-altruistic allele, it has the same selective advantage as the fully altruistic type.
Why?
Because the altruism allele is dominant and they have the same phenotype.
Oh, right.
So the cheater allele can hang around. It'll spread to like a really high frequency, but not totally fixed. What I realized was Hamilton calculated what Fisher called the average effect of a gene substitution. This is a really important population genetics concept, but Hamilton never said that that's what he did. I don't think he realized that's what he calculated. Some people since that time have done some models of haploid genetics and pointed out that the so-called inclusive fitness effect RB minus C is equal to the average effect of a gene substitution in that situation. But nobody's ever said, why is that important? Well, what I realized was when you look at dominance, you go from fully recessive to additive to dominant. Well, if it's additive, then the average effect of a gene substitution is equal to the RB minus C of a haploid model. So what they calculated for a haploid model then is the same thing for the diploid genetic with additive gene action. So that means Hamilton kind of extrapolated to diploid genetics, but it's actually true that holds. Now, when you go to dominance, if it's dominant, I think it's like 1 minus the allele frequency times RB minus C is the average effect of a gene substitution. So it's frequency dependent. And then if it's recessive, it's the allele frequency times RB minus C is the average effect. So if the allele frequency is 0, the average effect is 0. So the average effect then depends on allele frequency. And then if you have something like what they call the greenbeard effect, which is discriminating on the altruism locus itself, then the average effect depends on B minus C and allele frequency, but not on R. And so you can have altruism evolve among non-kin. So with the greenbeard effect, you can have RB minus C is less than 0, and yet the altruism allele is favored. So what inclusive fitness theorists have done is they typically defined R, B, and C so that RB minus C plays the same role in models as Fisher's average effect of a gene substitution. And they do that in several ways. It always involves manipulation of terms. Sometimes they'll have an equation of allele frequency change and then define RB and C so that they're defined in a way that they must be proportional to the rate of allele frequency change and indicative of the direction of selection, as Fisher's alpha is, or the average effect. But then they're left with these quantities, R, B, and C, that don't mean what Hamilton defined them to mean. They're no longer measurable. When you do this, you can kind of claim, oh, Hamilton's rule applies to anything. Inclusive fitness explains everything. The empirical researchers that were actually testing Hamilton's rule, they thought, oh, well, Hamilton's rule can apply to anything. And so they applied it haphazardly and with a broad brush. The whole point of all this math is to be able to look at the empirical work and see if anybody's actually tested it.
Well, it sounds to me like what you're saying is that Hamilton's rule, quote unquote, is just this very simple formula where the terms have been taken to be defined differently in a lot of different studies so they can kind of shoehorn it into the data that they've got and make it, if we say R is this, if we say C is this, and we do this, well, then RB minus C, then it works. Yeah. Well, so that's what
that's what the theorists do, right?
Right.
But then the empirical researchers, they use the normal definitions of those terms and they actually try to measure it. But then their problem is because they've come under the impression from the theorists that Hamilton's rule can apply to anything, they're not very careful in what they apply it to. So their problem is not in employing the wrong definitions of those terms. It's like how they apply it. And then there's also a problem of how they go about measuring B and C when they're applying it, because they're behaving as if they're applying it to altruism, but they're actually applying it to something else, which means that they're not calculating the terms correctly. Right. But if they use the definitions of terms that they say they're using, relatedness as genealogical relatedness, and the B and C as the phenotypic benefits and costs of altruism, and they actually measured those things correctly, then they would be testing the right original version of Hamilton's rule that's falsifiable and it's simple and all that.
But they just don't do that.
Yeah, they don't do that. I think a big reason is that because the theorists are always manipulating it, saying it applies to anything, but they're talking about something that's not really the same thing.
I mean, hopefully your paper can provide a more rigorous definition for R, B, and C in those contexts and delineate the situations and types of organisms and types of genes and stuff that it can actually apply to, because then you could test it.
So in this paper, I have enough room to kind of give several examples and point out where things have gone wrong, I think. But we need a lot more theoretical development of empirical applications. Instead of arguing about inclusive fitness, which is what they've done for 50 years, the theorists need to focus on how the heck are we going to test Hamilton's rule, given the constraints of real world situations where it's hard to determine all the interacting parameters and disentangle things, and think about systems where you can actually test it. We need clever techniques.
I mean, you're a theorist. Maybe you can propose some types of experiments like that in your paper.
I am.
Well, I look forward to reading that.
Well, thanks for being on the show.
All right.